Why hello lovely humans, Jen Foxbot here. In today's episode of Math Mondays, we are tackling partial derivatives. Yeah! Alright, so why partial derivatives? Why now? You're taking a break from the Schrodinger equation. Yes, because solving the Schrodinger equation requires a pretty good understanding of some advanced calculus topics. So I wanted to take a step back from solving more complex examples with the Schrodinger equation and really make sure that we have a solid understanding of some of the mathematics that are required to figure out what's going on in the Schrodinger equation. And one of those key concepts is partial derivatives. Yay! And really, derivatives in general. So I'm going to break this into two parts. The first part is going to be a review of derivatives. And the second part is where we really dive into partial derivatives and talk about what they mean, how we do them, and what some of the notation is. Cool. All right, here we go. So first, what is a derivative? I've done a few videos on this, but it's nice to kind of get a refresher. So, when we are talking about derivatives, oftentimes we're talking about some sort of function. Let's say we have a variable y, which is a function of x. I wrote that a little funky, so I'm going to redo that. So y is some function of x. And what this means is that y depends on x. So as x changes, it is going to determine the value of y. So if I were to make a graph like this, and x is on the horizontal, y is on the vertical, maybe I have some equation like this, where we have y just equals x. So I could ask, okay, for a given value of x, what is the value of y? So let's say we have x equals 2. I can either use the plot of the graph, this line, or I can use the equation. I can plug in x equals 2 and solve for y. In this case, it's a pretty trivial example. I would just get y equals 2. Pretty cool. So what derivatives allow us to do is to ask, what is the slope of this line? Or, alternatively and equivalently, what is the rate of change of y with respect to this variable? So that is what this means, dy dx. It equals the slope, or, like I said, this is the same thing, or the rate of change of y with respect to, woo, that's moving, with respect to x. Okay, so, to really understand this, it helps to make some comparisons. So let's say that I have another equation here. In this case, I'll call this y1. We'll say y2 equals 2x, and then y3 equals 1/2 x. And so if this were, say, the graph of 3 people moving over time, I might ask, okay, well, which person is moving the fastest? If they are going the same amount of distance, who will reach their destination first? So to do that, I could use the derivative. So we're going to take the derivative of y1, so dy1 dx. In other words, how much is y1 moving with respect to x? And since we just have x to the first power, we get 1. And the second one would be dy2 dx. The derivative of 2x is just 2. And finally, we have dy3 dx, which is just going to be 1/2. So if we wanted to say who's moving the fastest or whose rate of change is the most, we say, oh, well, y2. y2 is moving the fastest. They were in a very big hurry. And maybe we could say, okay, well, y3 was meandering home, smelling the roses. Maybe they found a butterfly that they followed for a little while. And then y1 was kind of moving at a constant, well, I guess they're all moving at a constant pace, but y1 was traveling at a reasonable pace. Not too fast, not too slow, right in the middle. So, why do we care about rates of change? Well, they pop up all the time in physics and engineering. It's just how the universe works. We're often talking about how things are changing over time or over space. So for example, velocity is how fast we're moving, how far we move over a given amount of time. Acceleration is how fast our velocity is changing or how much our velocity is changing. there are also rates of change in all sorts of other things. So if we have a hot object, we can ask how fast is the rate of cooling, or what is the rate of cooling. If we're trying to heat something up, we could say, what is the rate of heating? We also can talk about diffusion, or for example, if we were to drop some food color into water, we could ask, what is the rate of diffusion, aka how does the food dye diffuse into the water over time? And lots of other rates of change. So derivatives, super important. The other thing that I want to mention is that derivatives also allow us to find maximum and minimums. So in this case, it's a little bit trivial because we have a straight line, but maximum and minimum would come into play when we have something like this, where we have y equals, I'll label my axes, y equals x squared. So in this case, if I wanted to find the minimum, which would be here, this occurs when our slope is 0. Or in other words, when dy dx is 0. So if I find the derivative, which is just going to be 2x, and I set it equal to 0, I can find the point at which we have a minimum. And that point happens at x equals 0. And then what I would do is I would plug this back into the formula for y, and I would say, okay, well, when x equals 0, y is also 0. So in this case, the minimum occurs at 0, 0. And this will change depending on the formula that you have. Yeah, derivatives are super useful. One last mention about derivatives, one last thing to mention, is that derivatives also allow us to find the power series for a particular function. And if you're like, wait, what is that? Quick reminder, a power series looks like this. So if we have some function of x, we have a n, x to the n, which we would fill in like this, a0 plus a1 x plus a2 x squared plus a3 x cubed plus et cetera, et cetera, et cetera. So derivatives help us determine this for a particular function of x. And if you're like, what? Don't worry about it. It's okay. It's only really for specific applications. Cool. Okay, so now that we have done a pretty thorough review of derivatives, we can tackle partial derivatives. And partial derivatives deal with a situation in which we have a variable that depends on two variables. Ooh, so fun! All right, so check out part 2 where we dive into partial derivatives. Yay!